All right, in this lesson, we are going to construct confidence interval for a population mean. And part of that is going to be to find our critical value, which is now T star. So recall from our past lessons that we know a confidence interval is a point estimate plus or minus our margin of error. For proportions, our point estimate was p hat, and our margin of error has two parts, a critical value. But for proportions, that was z star. And our formula we should recognize from chapter 7 is p 1 minus p over n. But we don't have p, so we use p hat instead, which leads to this being called a standard error instead of a standard deviation often. All right, so for today, we're going to be calculating or constructing confidence intervals for means. So our point estimate is going to be x bar. And our critical value is no longer going to be z star, it's going to be t star. So we'll learn how to calculate that today. And our standard deviation formula, you may remember from chapter 7, is standard deviation over root n. Now we don't have our population standard deviation, we have our sample standard deviation, and that'll be divided by root n. All right. So we will find the standard error. Again, standard error is just talking about our standard deviation of the sampling distribution of x bar, but we're just going to be having our statistic instead of our parameter in that formula. So we're going to find that critical value, which is our t star. And we'll look at similarities and differences between the t distribution and the z distribution, which is the normal curve. All right, so let's get started. So recall our symbols for population mean is mu, and sample mean is x bar. So in this section, we're going to talk about estimating mu, which is our population mean, our parameter from the population, and our point estimate for mu is x bar. Remember, we have our same conditions, random, independent, and normality. Our random, it's either stated or it's not. If it's not, we could say proceed with caution. Remember that if they tell us of a bad sampling method, or if it were our own study and we realized that there was some form of bias in that sampling, maybe under coverage, there's no math that can fix that. You would have to throw the sample out and start again. So proceed with caution. Independent is our 10% rule. The way we calculate that is we say 10n has to be less than or equal to the population. Again, the reason that we do that is so that we're able to calculate standard deviation or our standard error using our formula. If this condition is not met, we can't proceed. For normality, the way this reads is that there are 3, but if you'll recall from chapter 7, there are really 2. So we have 1, 2, and this is just like it's not met, this last one. So they either tell us in the problem that the population distribution is normal, and if so, great. Or you can have a sample size large enough. So if your sample size is greater than or equal to 30 by CLT, our condition has been met and we may proceed. We only need one of these, just one. Just one of these two is enough to be able to continue on. If the population is not stated as normal, so we didn't meet number 1, and our sample size is under 30, we also didn't meet number 2, then our normality condition is not met, and we cannot construct a confidence interval. Remember, the reason we're using normality is so that we can use a normal curve. Now, this time we're actually not using a normal curve, we're using a t distribution, but it still requires this condition to be met. So now a little bit about that t distribution. All right, so our confidence interval is the point estimate plus or minus our margin of error. Our point estimate is just our statistic. Our margin of error consists of 2 parts, critical value and standard deviation. Remember that our formula for standard deviation of the sampling distribution of x bar was population standard deviation over root n. But if I don't even know what mu is, I'm probably not going to know what the standard deviation of the population is. And so instead, we have to use our sample standard deviation, S of x. And that means we're going to have more variability. So because of that, we have to have a larger z star. So when calculating confidence intervals for mean, we're always going to use the t distribution instead of the normal distribution. Now, the good news is the process is almost exactly the same. And we'll get to that on the next sheet. Characteristics of the t-distribution. So notice over here at right, there are some pictures of this distribution, and our degrees of freedom is just n minus 1. So it's just your sample size minus 1. Now, if your degrees of freedom equals 1, that's this bottom one. Remember, the area under a density curve is equal to 1. So if it is shorter, it has more variability. So it has more area in the tail, which means we're going to have a larger t-star, a larger critical value, which means we're going to have a wider interval, which is often not what we want to have. But as our degrees of freedom approaches infinity, meaning as our sample size gets really large, our t-distribution actually becomes normal. It's like it approaches that normal curve. So here's some characteristics of the t-distribution. It's symmetric. And it is bell-shaped. I left out an M. It's metric. And it has more variability than the normal curve. It means it's shorter and more stretched out than the normal curve. And that is going to give us a larger value for our critical value. Okay, so we're going to use t-star instead of z-star. And here it tells you that to use t-star, it's still under second vars, but it's going to be just below. It's number 4. So when I go in my calculator, second vars, here's inverse norm. We're just going to go 1 below. Notice what it asks us for. It asks us for area, just like inverse norm. That's area to the left, so we're going to calculate the same way. But it also asks us for degrees of freedom, which is just n minus 1. So the only additional thing we have to do for this calculation is to give a degrees of freedom. So let's do these 3 problems together. So we're going to find t-star for 90% confidence interval, so 0.9. So we're going to go t-star equals inverse t, and we need 2 things. We need area to the left, which is going to be 1 minus 0.9 divided by 2, which is 0.05. Notice that feels just like what we did for confidence intervals with proportions. And then now we have to give this second part, which is degrees of freedom. So our sample size is 14. So our degrees of freedom is 14 minus 1, which is 13. And then I'm going to type it in. So my degree to the left, or my area to the left is 0.05, and my degrees of freedom is 13. And I get 1.77. Just like z-star, these are normally rounded to the 100th. Notice it also takes your calculator a little longer to calculate your t-star than it does for z-star. Just for fun, I'm going to use it. I'm going to find my z-star for the same value. So 0.05, just for funsies. And notice it should be smaller than the t-star. And it is. Remember what we just told you? We needed a larger critical value for t-star, and our t-star is larger, 1.77, than our z-star would have been for the same area to the left. So you can expect that to be the case. And also, just for fun, watch as your degrees of freedom increase. So if I were to make my sample size larger, this value is going to get smaller. So my critical value will get smaller. And notice it is smaller. My original with a degrees of freedom of 13 was 1.77. But when I increased my sample size, my t-star went down, which is going to happen because as our sample size approaches infinity, gets really large, it's approaching that normal curve. So it's going to get closer and closer and closer to z-star as our n gets larger. All right, so let's go ahead and do the next 2. So our t-star equals inverse t, and we're going to need area to the left and degrees of freedom. So we have 99%. So our confidence level is 0.99. Our sample size is 51, which means our degrees of freedom is going to be 1 less than that, so 50. So we have our degrees of freedom is 50. And let's calculate that area. We'll go 1 minus our confidence level divided by 2, which is 0.01 divided by 2, which is 0.005. We'll type that in. So we're going to go second vars, inverse norm, 0.005 Oops, I went to inverse normal. Second bars. Inverse T. Our area to the left is 0.0005. Our degrees of freedom is 50. It takes it a second to calculate there. And then we got 3.49, but this is 6. I'm going to round this up to 3.50. So T star equals 3.50. So if you would like to take a moment and pause the video, you could do C yourself. All right, so checking your work, you should have inverse T. Your area to the left should be 1 minus 0.95 divided by 2, which is 0.025. Your degrees of freedom should be 1 less than your N, or 44. And when we type that guy in, we have second bars, inverse T, 0.025, and then 44. And I got 2.0, now I'm going to round up to a 2. 2.02. 2.02 for my T star. All right. So the formula for a confidence interval for means is point estimate, which is X bar, plus or minus my critical value, which is T star, and then our standard deviation, which is going to be standard deviation from the sample over root N. So let's go ahead and let's calculate one of these by hand. The Trial Urban District Assessment, TUDA, is a government-sponsored study of student achievement in large urban school districts. TUDA gives a reading test score from 0 to 500. A score of 243 is a basic reading level, and a score of 281 is proficient. Scores for a random sample of 1,470, so that's our sample size. 8th graders in Atlanta had a sample mean, so they gave it to us here, of 240, and a standard deviation of 42.17. Calculate and interpret a 90% confidence interval. All right, so find the point estimate. So our point estimate in this case is X bar. They gave it to us. It's 240. It's a score of 240. Now we're going to check those conditions. We have random, independent, and normality. For random, they did tell us that that's a random sample, so it's stated. For our independence, that's our 10% rule. So that's going to be 10N, which our N is 1,470, which is 14,700. And that needs to be less than or equal to the population of all Atlanta 8th graders. All ATL 8th graders. Now, Atlanta is a really large city, but if you were the person running this study, you would need to make sure that there are more than 14,700 8th graders in Atlanta. I think this is reasonable. It's a big city. I think there are more. So we're going to say that seems reasonable. But if you were the person running the study, you would have to make sure that there are more than 14,700 8th graders. Otherwise, you would just need a smaller sample. Our normality condition, we have 2 options. The first option is that they tell us that the pop distribution is normal, that the distribution of all TUDA scores is approximately normal. They did not tell us that. So that condition has not been met, but we only need one of the 2. The second condition is CLT, and that's that N is greater than or equal to 30. Our sample size equals 1,470, which is greater than or equal to 30. So by CLT, we have met this condition. So we are good. We have met our normality condition. Now, the first step is to, so far, we have our X bar. So our X bar we've already got is 240 plus or minus. The next thing we would need to do is to find our T star, right? So our T star is going to be T star equals inverse T. We're going to go area to the left. So we're going to go 1 minus 0.9 divided by 2, which is 0.05. And we needed degrees of freedom. Our degrees of freedom, since our sample size is 1,470, it's going to be 1 less than that, 1,469. And so I typed that in. So I'm going to go second bars, inverse T. My area is 0.05. My degrees of freedom is 1,469. And I got 1.65 equals 1.65. So now we have that T star, 1.65. Now we just need to find that standard deviation. That's what they asked us to calculate next, the standard deviation of X bar, which is also known as the standard error. Okay, so and that formula is, which in this case is not, it's really standard error because we don't have standard deviation. We have S of X. It's going to be over root n. So our standard deviation of the sample equals 42.17. And our sample size is 1,470. So I'm going to type that in. So I have 42.14, and I have the square root of 1,470. Oops. Notice what I did. I misread my writing. That is a 7, right? Yeah, oopsie. So I really meant 7. So I got 1.09987. So I'm going to call that 1.10. Okay. Find the margin of error. Remember, our margin of error is, so here's this guy, 1.10. So our margin of error is just my T star times my standard error or my standard deviation of X bar. So I just multiply these two numbers together. So I have 1.65 times 1.10. I'm actually not going to use that rounded value though. I'm going to go 1.65 times, I'm just going to scroll up and grab my non-rounded. And I get 1.815. 1.815. So all we did just now is just calculate my margin of error. My margin of error is 1.815. Now it said construct that interval. So remember, to construct the interval, we just take our point estimate, which in this case is 240, and we subtract my margin of error minus 1.815 to get that lower value. And to get my higher value, I'm going to take my point estimate, 240, and I'm going to add 1.815. So in my calculator, I'm going to say 240 minus my margin of error, and I get 238.185. And my higher value, my upper bound, is 241.815. Okay, interpret this interval in context. We will say, we are 90% confident that the true parameter, and in this case, our parameter is the true mean score of all Atlanta 8th graders, the true mean TUDA score for all Atlanta 8th graders is between 238 and 242. I rounded in my estimate, or you could have given all of the decimals there, but so I am 90% confident that the true TUDA score for all ATL 8th graders is between 238 and 242. So here's a question. Like we asked some of these back for proportions, like understanding what this, how could this be helpful? So imagine I am a superintendent for these Fulton County schools for Atlanta, and I want to know, how are these 8th graders doing? Notice a basic reading score is 243. So I could ask now, so even though the mean is 240, which is below the basic reading level, I know that every time I take a sample, I'm going to get a different X bar. But the whole purpose of creating a confidence interval is to give a plausible range of values. So this is our plausible range of values, is 243 in this interval. It isn't. This interval of values is well below 243. So how are those readers doing? Well, the mean TUDA score is below basic. So anyway, that is something that we can tell by looking at this confidence interval. So we're 90% confident that the true mean TUDA score for all ATL 8th graders is in this interval, and this interval is below basic reading level. All right, let's look at the next. Oh, that's all. And that is all for this lesson.